So the word dielectric refers to a property of a material. And those materials are often referred to as dielectrics. So examples of dielectrics are glass or oil, paper. It's really any material, and well, not tends, but these are non-conductor materials. So these are insulator type materials. Although you can honestly talk about the dielectric property of a metal, but it's honestly really boring because it's sort of the ultimate dielectric. But anyway, so it's a property of a material, and it's often given a quantification. So it's quantified by a letter called kappa. And kappa is a Greek letter, and it's like the lowercase version. And the way you spell the name of the letter is K-A-P-P-A, so kappa. So lowercase Greek letter. I'm not sure who introduced kappa the first time. It could be all the way back to Faraday, Michael Faraday, but I don't know. So yeah, so the dielectric quality is quantified by this number kappa. So let me tell you how to understand this. So imagine that you have actually let me describe. So I'll just take one of these materials, and you could have in mind glass, for example, a piece of glass. So I have this piece of glass, right? So this is my dielectric, which if you look, Di means 2. So this is like a 2 electric. So that name, it's the technical word, must come from something back in the day. But I'll say that this material is described by this number called kappa. By the way, kappa actually has no dimensions. I'll show you. It doesn't have units. Kappa is a pure number, a real number. Okay, so here's my dielectric. And if I put this, so no electric field. So this object is actually quite boring. No interesting charge. Right, so there's nothing interesting about the charge. What's a dielectric becomes really interesting when you consider having an electric field. So let me imagine having some electric field, and to start this discussion of dielectrics, I'm going to have a really easy, uniform electric field that you might find within a parallel plate capacitor, or because of two infinite conducting sheets that have charge, or something like that, which is, honestly, it's also a capacitor. So I've got this electric field, and it's in vacuum. Vacuum, another word for that, is also known as free space. And what we're going to do is we're going to consider putting this dielectric in this electric field and talk about the electric field within the dielectric when the dielectric is in this new environment, not this old, really boring environment, but this new environment. So let's put it there. So here is that dielectric. I just immerse it in this background electric field, E sub 0. So here's the dielectric. And what it does is it has a dielectric response. And this is what makes a dielectric a dielectric. What happens is this thing is full of, it's made out of atoms, and those atoms are little charged, are full of themselves, full of positive and negative charge. And what this dielectric does is it is not a conductor, but it can separate charge very slightly. So I'm going to put blue. So this is meant to be a blue color. So there's a slight blueness that shows up as a positive edge on this non-conducting dielectric slab. And because I imagine this thing starting off with no net charge, I can imagine that the same amount of negative charge shows up in the back end. And so this dielectric has polarized, right? And it's the electric field that it's immersed in that causes that polarization. And so this field is actually, if you look, this external field is inside the material, right? Materials don't block electric field. The electric field goes everywhere. But what happens is because the dielectric polarizes this way, the dielectric has a dielectric response electric field. See this charge right here? There is other field inside of here. So I'm going to draw it sort of vaguely like this. And this would be, say, the response by the field. And so we can say that inside of the dielectric, is a new electric field. It's the result of the superposition, right? Superposition means summation strictly. But I might say that this is because, and I'm going to give it a special set of initials. This right here is the field of the bound charge separation in the dielectric. Bound charge. This is the BC. Right? So there's this electric field due to this charge right here. This is the bound positive charge. And this right here is the bound negative charge. So yeah, you've got this, and it's considered bound because it is not free. It's not like a conductor, right? This thing right here, this dielectric, is non-conducting. So the charge can't flow around willy-nilly. It's kind of stuck in the material, but you can have a very slight polarization dielectric response. And because of that dielectric response to the field, it's the E naught that causes the response. And associated with that response is charge separation, and whenever you have new charge separated, you get another electric field. Now the thing is the electric field due to this bound charge is opposite direction to the electric field that caused the bound charge, right? So this electric field, E sub 0, takes a plus charge and presses it towards the right, and the very same field takes a negative charge and pushes it leftward. And that's why we have this bound charge polarization, dielectric response. And the electric field of that bound charge points from the positive charge to the negative charge. So that's a new electric field. It's the dielectric response, and it is backwards to the field that induced the polarization. And so the net field within the dielectric, this is not outside the dielectric. Outside the dielectric, actually, we still have the electric field E naught. E naught is out here. E naught is over here. So the only new thing is within the dielectric, we get this E sub bound charge, and the net field goes like this. And what happens is, because the net field is the combination of those two things, also the bound charge electric field is going to have a magnitude that is smaller than the electric field's magnitude that induced the polarization. So the dielectric response is weak in a sense. This net field within the dielectric is equal to, and this is where this number kappa comes in, the dielectric's sort of quantification. It goes like this: 1 over kappa of the electric field that caused the charge separation, that caused the dielectric response. So this number kappa, in this modeling of a dielectric response, honestly, this is a very simple estimation model. Not all materials actually do this all that closely, and engineers would need to model a dielectric response, more carefully. They'd have to do some testing and some engineering, and kappa could depend on lots of things, including temperature. This could be a part of a way deeper story, but for the purposes of this video, we're just going to say that kappa is a number that is bigger than 1, and for vacuum, we'd say that kappa equals to 1. Okay, so I think this is a big deal here. So you can actually go and you can actually kind of see that how you might get the electric field response, or the response electric field, because you have the relationship between the net field inside of here. So this is the net field, which is the result of the external field and the new internal field. So that's the net field. So you could solve for the field due to the bound charge alone if you wanted to. But this is the story. So you can get materials. So kappa of air is really close to 1. It's like 1 point, I think it's like 4 or 5 zeros and a 5. You notice that there are no units, right? No units. Yes. But you can have materials that, I've seen some quoted in a book where, like, some exotic material could have kappa of like 60, or maybe, no, 600, I think I saw in a book, or something like that. So some exotic material can have a large kappa. So you can see, like, if you use this really exotic material, kappa 600, then, oh, interesting. Actually, I need to think about kappa a little bit. So, anyways, let's play this out. So if the kappa is this exotic material, really large value, then the net electric field is 1 over 600 times the external field. That is, the field on the inside of the dielectric is really small compared to the external field. And so for this, exotic kappa, or exotic material, can almost completely hide the external field. So let me yes, so I think that's the right idea. So check this out. Kappa for a conductor needs to be infinity. Because if I put in 1 over infinity, because of all the conduction electrons in the material, the electrons will move and keep moving and keep moving and keep moving until there is no more electric field left to cause any more electrons to move. And so for conductors, we should have a dielectric response that's infinitely good at hiding external field. That is, within a conductor, there is no field because there is no net charge anywhere, anywhere that you check in a conductor. Okay. So the next piece of the lecture here is to talk about using dielectrics in a capacitor. I think that this is the original situation, so capacitance is the original situation where a scientist long ago, Michael Faraday, who the unit of capacitance is named after, right? Michael Faraday, whoops, misspelled this incredibly important person's name, so Faraday, and the unit that we're using for capacitance is called the farad, right, given the symbol capital F. But it's named after this person who studied different materials in a capacitor and tried to understand what happened to the capacitance if materials were included, dielectric materials. Yeah, so it turns out that using a dielectric in a capacitor, in general, what it does is it increases the capacitance. What this means, like if you were to increase capacitance, that means that for the same potential difference, let's say that you could only ever use, say, 1-volt batteries. If you include a dielectric in your capacitor, with that 1-volt battery, you can store a much larger charge separation. So that's the idea. All right, so let me describe some stuff. So let's put a dielectric in a capacitor, and this is, so we're going to study the problem of dielectrics in capacitors with parallel plate capacitors. So this is parallel plate geometry. And just really quickly, I'll remind you that if you have a plate of area A and separation distance D, and what's in between is vacuum. So vacuum has kappa equals to 1 in a dielectric sense. So vacuum's not a dielectric. It's not got any dielectric quality. So, but the point is the capacitance is written this way. It's epsilon naught times A divided by D. Right, so this is the answer in the vacuum. Yeah, and remember that also this is the charge per potential difference. So Q per V. That's the definition of capacitance. Okay, so so the ratio of the charge you can separate for a given voltage is equal to epsilon naught A over D. This capacitance is independent of the charge and the voltage, but it turns out it's dependent on the ratio of the charge per voltage. Yeah, some language like that. So anyways, so easy example, and we'll have more complicated ones in a second. It's to completely fill the cap's volume with a single dielectric material. So I'm going to denote the dielectric material by its dielectric constant called kappa. And the drawing looks like this. So we still have the two plates. So here's the plate of area A and the lower plate also of the same area because this is a parallel plate capacitor, and the distance d is still the same distance, but what we have in between is a material. So let me just shade it in red. So there is a material in here called a dielectric, and it fills the space completely. This is the idea. And what I'm going to imagine is I'm going to, because a capacitor, right, we imagine separating the charge Q. So let me separate some charge there. And what I'm going to do is I'm going to calculate the electric field in the dielectric. So the electric field, right, is going to be equal to 1 over kappa. So since kappa is bigger than 1 in a dielectric, we know the electric field in a dielectric is smaller than the electric field you would have in the vacuum, if there was vacuum there instead. So let me put E sub vacuum. And this is, so I'll put the 1 over kappa. And the electric field in a vacuum, I've got two parallel plates of opposite sign. So I would have a big electric field that points from Q towards minus Q that's uniform in this parallel plate capacitor. So I'll cut to the chase. The electric field in here is sigma over epsilon naught. That's the electric field in the vacuum between Q and minus Q. That's what you would have up here, is sigma over epsilon naught. Sigma is the charge per unit area, and there's the charge and there's the area. So I'm going to replace sigma by Q per A. So this is 1 over kappa, and then Q over A epsilon naught. Okay, so far I've used Q and A, kappa and epsilon naught. So I wonder, how does the D come in? The D comes in, D is how we get voltage, right? So don't forget that there is a relationship, and actually, I have to be careful, so let me put absolute value bars on the E and the evac, and I'm going to depend on us remembering that in a capacitor we tend to talk about the charge separation as the positive charge, so that's the positive area charge density associated with the charge separation across the capacitor. So I'm just going to leave it like this without absolute value bars anywhere else, but this really is magnitude stuff. So D is how we get voltage, and since E is uniform between the plates, calculating the potential difference, delta V, between the two plates is really easy. Delta V is simply E times D, where we're keeping track of the magnitude only. So that's the potential difference between the two plates, and now we have a reason to have D around. And so what this means is that I just need to take the electric field's magnitude, which I've said is 1 over kappa Q over A epsilon naught, and multiply by D. So this is 1 over kappa Q D over A epsilon naught. So that's the potential difference. And the capacitance with the dielectric is equal to the charge divided by the potential difference. So the charge is Q, but the potential difference is this thing on the bottom. So 1 over kappa Q D over A epsilon naught. And so I've got top divided by 1 over kappa, puts a kappa up top. And then the Q's are going to cancel. The A epsilon naught rises to the top when I do my quotient stuff, and the D is left over on the bottom. And if you look at this expression and you compare up here, you see that A epsilon naught over D is the vacuum capacitance. So maybe I'll refer to this as the vacuum capacitance for the parallel plate capacitor. So this is kappa times the capacitance that you would measure or determine for the vacuum. So all that happens is that the capacitance with the dielectric, if the dielectric fills the space, it's kappa times the capacitance as if we didn't have a dielectric. So this is something that maybe I'll put a box around. So, oops. So this is the capacitance if you have the dielectric, but let me caution you, dielectric fills the space, right? So I need dielectric everywhere within the plates, and that's what I'll get. So now, naturally, you might wonder, well, what if the dielectric only fills part of the space in there? So let me show you what you would do in that case. So if dielectric, what if dielectric only fills part of the space? Okay, so I'm going to do sort of the next easiest thing. So the next easiest geometry looks like this. I'm going to take the capacitor that we imagine starting as all empty vacuum and putting in a dielectric only in part of it, not necessarily half of it, but I'm going to put it in part ways, like this. And so I need to specify, so let me draw a little like, maybe I'll say it goes across like that. So not necessarily halfway full, but I'll say that the distance that the vacuum occupies is A, and then the distance that the dielectric occupies is B. And so the total distance is A plus B. So just like before, right, in order to get the capacitance, what I do is I just imagine a charge separation Q. So let me imagine that charge separation. Here's Q and minus Q. Understand the electric field everywhere. Then, because I know the electric field, calculate the potential difference, then get the capacitance equal to Q, which was my imagined charge separation, divide by delta V, which is what I end up calculating as the potential difference because of the charge separation. So that's how I'm going to get the capacitance. This is the recipe every time. Actually, this is how you understand capacitance. So let's imagine charge separation. Here it is, Q and minus Q. Understand E everywhere. That's the next step. So early on in this lecture, I said that what happens when you insert a dielectric is you may have started off with a field E sub 0 filling your vacuum, right? So there's E sub 0 everywhere. But inside the dielectric, there's going to be a response because of a polarization of the dielectric material. And so I'm going to have a different electric field inside of here, which is equal to E naught divided by kappa, right? So the electric field inside the dielectric is going to be whatever E naught is but divided by the number that's bigger than 1 for dielectrics, right? So the electric field in the dielectric is always smaller than the electric field in the vacuum. So that's what I'm going to use. So now I have understood the electric field everywhere. E naught, the thing to say is the electric field here, because of the charge separation Q and minus Q, that electric field it has a magnitude equal to sigma over epsilon naught, which is equal to right, Q over A epsilon naught, right? Charge per area is sigma, and then I divide by epsilon naught. So now I've understood E everywhere, and now I can calculate V. So delta V. Again, the calculation of delta V is easy because the electric fields are uniform, sort of parallel across, so it's not uniform all the way across, but the idea is while I meander from, say, the low plate up to the upper plate, and I go backwards against the electric field direction, what I'll do is I'll end up, I guess should I do it? Let me just tell you what the answer is. So, well, actually, yeah, so I'll show you. So let's start here. That's the starting point. Get to here. This is the finishing point. And what I need to do is integrate, right, the negative of whatever the electric field is, dotted with a small displacement, but the path, the journey, starts from S and finishes at F, right? So what this is, though, is the electric field has two values, right? I was kind of stuttering on the non-uniformness of the electric field. But the thing is on this path, I'm going to take the path to go up that way. So what that might look like is, so the negative of the electric field is down, so the negative of it is upwards, so that's up, and the little ds displacements that take me from down here to up there are also upwards. So the dot product is just negative E dot ds's, they're parallel, so these are all going to be positive signs. And so the electric field from start to here, you just go from 0 to b, right? You need to do b of distance. So this is going to be the integral from 0 up to b, right? So that's the distance where the electric field has this value instead, which is Q over A epsilon naught kappa, Q over A epsilon naught 1 over kappa, and then I'm going to multiply it. I'll just call this a dy, right? So the y direction, say, is upwards. But I'm not finished. I've only gotten to b. I need to continue and finish. But the thing is from b up to, actually, so this is kind of strange. Yeah, so I'll go from b to a plus b. That's what y is doing. So if this is y equals to 0, for the starting position, I'll go y equals to 0 to y equals to b. But once I'm at b, I need to finish the journey starting at b, and I need to go the extra distance a, so it goes from b up to a plus b. That's kind of strange looking, but that's a different electric field. It's the electric field in the vacuum, which is just Q over A epsilon naught, no kappas, dy, right? So that's the potential difference. And so if I finish this out, I've got what happens, 0 to b, right? It goes b q over a epsilon naught, and I'll put a 1 over kappa. And then I'll just cut to the chase for the answer. What this amounts to is a q over a epsilon naught, but no kappa. So this right here is the potential difference. And once I have the potential difference, right, this is the recipe, I just need to calculate C. So C is Q over delta V. Q is just Q. And then delta V is this business here. So it's 1 over kappa B Q over A epsilon naught plus, shoot. Well, you can learn something from my mistake. I didn't make this division symbol long enough. So let me start over and be really careful. So Q over delta V is Q over all of that, right? I was about to split it up, and that's a classic mistake people make when they're learning in this subject. You really got to take this thing and put all of it together underneath. So remember your order of operations. So this is 1 over kappa B Q over A epsilon naught plus AQ over A epsilon naught, right? And so you can see that the Q's are gonna cancel. So let me cancel some Q's. This is in general what's going to happen when you do capacitance stuff, because you had no reason to choose any particular Q, which means any particular Q doesn't matter. See, it always goes away. But the area and the distances and the dielectric material, those geometric and material aspects of the capacitance, they do not go away. And also the vacuum doesn't go away. So, anyways, what I get is 1 over kappa B over A epsilon naught plus A over A epsilon naught. That's what I get for the capacitance. And so this is really inconvenient, but check this out. I'm going to flip both sides upside down. So 1 over C equals, now this is, so check this out. This is a surprise. Okay, so 1 over C. So I flip everything upside down. All that means on the right-hand side is I just take the bottom and pretend it's the top, or I make it the top. So it becomes B over kappa A epsilon 0 plus A over A epsilon naught. Okay, so I'm going to clean this up a little bit. I'm going to call this the capacitance with whatever dielectric configuration I am solving for, right? And I'd like you to notice that this term right here is actually one over the capacitance in the vacuum if instead of a distance d, I had a distance a. So this is the vacuum capacitance, but it's 1 over. So this actually, if you look at it real close, this is 1 over the vacuum capacitance for the thickness A, and this is 1 over the capacitance in the presence of the dielectric over the thickness B. And this is the effective capacitance. This is the effective capacitance in series. So if you look again at this capacitor that we just saw for the capacitance, the effective capacitance with this like partially filled dielectric is actually the series combination of a vacuum capacitance over the distance A and a dielectric capacitance, filled dielectric capacitance over the distance B. So it looks like it's a series capacitance. So that's that geometry. It's sort of like partially filled in this way. So in contrast though, what if I did this? What if I have a capacitor where I have one type of dielectric and another type of dielectric, but I don't necessarily have an equal filling. I just know that I'm going to fill with one type on the left and a different type on the right, like this. So this turns out, right, that's a different configuration than this. It's got a really interesting difference. Up here, I found this was the series. It looks like just two capacitors in series. So this looks like a vacuum capacitance over A in series with a kappa dielectric capacitance over the distance or height B, right? This is series. This is going to turn out, I'll show you, it's parallel. Whoops, I misspelled that. But we have to be really careful in this setup. So let me show you about being careful. Okay, so let me draw this with some perspective. Actually, I shouldn't have drawn that yet. So let's see. This is the top plate, and I'm going to pretend, right, that these two zones are rectangular in there. So I'm going to make that dotted line, and then that boundary is here between the two dielectric materials. So here is one of the dielectric materials, and the other dielectric material is here, like that. And then the other plate, I won't, yeah, maybe I'll draw it anyway. So the other plate is here. So this is my capacitor arrangement now, right? This is the wire coming into the upper plate, and then the wire from the lower plate going away. And I've got the K2, this is the capacitance there, and this is the K1 capacitance. All right? So the strange thing about this is I'm going to say that this has area A2, so this is a little rectangular area. The other part, though, has the area A1, and A1 plus A2 is the total area of either plate of our capacitor, right? It's a parallel plate capacitor. What's more, though, is, and this is more strange, what I must have in this situation is that if I was to calculate the potential difference cannot be different through kappa 1 or kappa 2, right? The potential difference through kappa 1 and kappa 2 have to be the same, which means, in this particular case, that the electric fields through kappa 1 and kappa 2 must be the same. But if kappa 1 and kappa 2 are such that they are not equal, right, which is the sort of the point, kappa 1 and kappa 2 are not equal, then the charge density over the plate with area 1 and the charge density over the plate with area 2, they cannot be equal either. And so we've, in all these earlier situations what we did was we imagined that there was no reason for the charge density to be anything other than uniform, right? With a uniform charge density, with that uniform electric field. Oops, I'm off the screen. So we didn't imagine the charge density being anything different from uniform along there, so we get our uniform electric field. And yeah, it's like stuff was really simple. Even in this case, the electric field, the charge density didn't have any reason to be different. But up here, it's true, it turns out in this case, we want a uniform electric field so that when we integrate across the gap, we discover the same potential difference here and there, right? These are the same distances, so we need the same electric fields. But because the dielectric materials are different, we need different charge densities up and below. So this is what we're going to do instead. We're going to say that our upper plate has a charge which is equal to sigma 1 times A1 plus sigma 2 times A2. That'll be the total charge separation on this strange mixed dielectric parallel plate capacitor. So here is our charge assertion, our charge separation assertion, right? So we assert that charge. Okay, so we've got a sigma 1 and a sigma 2. We must have delta V across kappa 1 equal to delta V across kappa 2. And what this is going to imply is, because there's only one distance, like let's say the distance is D, because there's only one distance, if the voltages have to be the same, that means that the electric fields have to be the same. So the electric field inside of dielectric number 1 has to be the same as the electric field inside material number 2. Okay, so now I have those things. So let's see. So what can we do? I've all of a sudden lost my train of thought here. Just a second. Let me see if I can get it back. My notes aren't helping me here. So I've got this electric field. So the electric field, oh yeah, let's do this way. So the electric field in kappa 1 is, so I've got that charge, and I want to ultimately calculate the effective capacitance here. And the effective capacitance is the total charge separated divided by the potential difference. And I've got this. So let me work it. I got to put that up there. Okay, so E1 must equal to E2, and E1 is equal to 1 over kappa 1, what I would get with E0, right? That's the vacuum electric field, and that's the 1 over kappa 1 on this side. So 1 over kappa 1, and then the electric field in the vacuum if the charge was sigma 1. Yeah, let's do that. So it'll be sigma 1 over epsilon naught. That's the electric field in the vacuum with that charge density. And over with E2, what I get is it's 1 over kappa 2 instead of what the vacuum field would be. And the vacuum field would be a different sigma over epsilon 0. Okay, so, and I know that these two things must be equal. So if they are equal, I can say something about sigma 1 and sigma 2's relationship. So E1 equals E2, so then, oops, that's not a kappa 0, it's a kappa 2. All right, so E1 equals to E2 means that 1 over kappa 1, right? So E1 equals to E2. Here's E1, here's E2. So I'm going to set this and this equal to each other. So sigma 1 over kappa 1 must equal sigma 2 over kappa 2. The epsilon naughts are common to both sides, so they disappear from both sides, right? So this is what delta V being the same across that gap and that gap, right? Because these are conductors, and the potential difference between these two conductors, they are equipotential volumes, right? The conductors are. So they have the same potential no matter what path you take. Okay, so I get this thing that the relationship between sigma 1 and sigma 2, so sigma 2, let me go ahead and, sigma 2 has to be kappa 2 over kappa 1 on sigma 1, like this. So all of Q is equal to sigma 1 A1 plus sigma 2 yeah, let's just do it that way. So sigma 2, which is here, so K2, or I mean kappa 2 over kappa 1, sigma 1 A2. So that's the total charge. Yeah, and it's in terms of A1 and A2. Okay, so delta V is simply, I've got that distance d, and I can choose either E1 or E2. Let's choose E1 because everything in terms of sigma 1 here, and E1 has the sigma 1. So delta V with E1 is, right, it's going to be E1 times the distance d, right? That's the result of the integral. So this is, so E1 is 1 over kappa 1, sigma 1 over epsilon naught times d. Okay, so that's delta V. And then if I go and calculate the capacitance, the effective capacitance, it's equal to, so it's the total charge separated, this thing right here, which I've rewritten here, divided by delta V. So here's this, it's sigma 1 times, it goes A1 plus kappa 2 over kappa 1. Sigma 1 I've sort of divided out together, times A2. And then I divide by, right, delta V, and delta V is this business here. You see I've got sigma 1 times D over kappa 1 epsilon naught. Okay, so what this gives you though is, so you can see that the sigma 1s are going to cancel like that, and the kappa 1 epsilon naught is on the very bottom, so it's going to go to the top and D will stay below. So I can write that the C effective is equal to, it goes, so A1 plus kappa 2 over kappa 1 A2, and I multiply by kappa 1 epsilon naught, and then I divide by D. D stays in the denominator, and what you get is, so you can see the kappa 1 hits the A1 with an epsilon naught, so it goes kappa 1 A1 epsilon naught over D plus kappa 1 and kappa 1 here, they cancel when I multiply this on the second term in the brackets. So it goes kappa 2 A2 epsilon naught over D. This is C effective. And if you look, this could be a C associated with kappa 1 plus a C associated with kappa 2, and I get an effective total capacitance where C sub kappa 1 is as if I just considered the capacitor with area A1 and distance D, like thickness D. So this right here looks like the parallel rule, which I said we were going to get, where on the right I have that K2 dielectric, and on the left I have the K1 dielectric. This has area A2, dielectric kappa 2, distance or thickness D. This has area A1, dielectric constant kappa 1, and also thickness D. You get the parallel rule. But it hinged on, right, it hinged on the fact that I needed to remember or to know that the charge densities above the two dielectrics are in general different.